Okay. And I go here. 275. Insert. We are on the case. Okay. Everyone's good with the attendance? Okay, I'm going to get back to it. Just wait like a few more seconds for your friend. Good? Perfect. Before I start today's lecture, any of you have any questions? No? And as I said, based on your availability that you filled out in the questionnaire that I gave last session, I started to have tutoring sessions. And if you have F or D on the previous exam, I highly encourage you to attend those to get extra credit. But I'm also going to record them and upload them on YouTube. So if you cannot make it, you at least can watch the video. I know when you have, now 30th lecture, so if you want to watch 30 hours before your exam is not feasible, but maybe watching 5 hours summary of everything would be more feasible, and you'll do that. So, and I sent announcements on Canvas, and I sent yesterday too, so be tuned. Didn't do the attendance. And you have like your homework due tonight, so remember to do your homework if you didn't already have done so. You haven't already done so. Okay, so today I'm going to try to finish chapter 4, and I'm not going to cover everything. As you saw, I'm kind of pick and choose what to teach because I want to go through more chapters. You understand them and not going too fast, too slow. But I specify the parts that I'm teaching, right? For instance, here I say 4.3, so you know what section of the book you read. And as I said, I mandated for you guys to have the book, but I know however much I emphasize, or like lots of you that you don't have the book. But I had like friends of yours coming to my office hours or like tutoring sessions, and then they tell me that now that I'm reading the book, everything makes much more sense. So I highly encourage you all to read the book. So now today we're going to talk about resonance model for benzene. And in chapter 1, we talked about resonance structures. Can anyone remember what was the definition of resonance? What do we mean when we say two molecules are resonance of each other, or one specific compound has a resonance structure? Anyone? And I kind of have the description here too, so if you want to refer to it. Yes? Exactly, you have structures that they're the same, but the arrangement of electrons are different. And anyone remembers how do we denote arrangement of electrons? How do I show electrons when I have two atoms, right? How do I show electrons between, around them? What's that? Yes, Lewis structure. So what did you want to say?
I didn't say Lewis structure.
Yes. So for instance, if you had like CO2, remember? Let me have another color. For instance, CO2, if you want to write the structure, you have like carbon, 4 valence electrons around it, right? This is Lewis structure for carbon, and then for oxygen, let me write another color. The valence for oxygen is 6 because it's in group 6A, like 1, 2, 3, 4, 5, 6. And then the other oxygen, like 1, 2, 3, 4, 5, 6. And when we want to form bonds, each 2 electrons, they form a bond, right? So these two, for instance, these two. But this structure, as I wrote, is kind of ugly, right? So what we do, we write the Lewis structure for carbon dioxide like this. But I kind of write each of them separately, so you see the arrangement of electrons for each of the atoms. Does that make sense? And I went through these in more detail in the video that I posted yesterday on Canvas on their like tutoring sessions. So if you have difficulties with these, I encourage you to study because you're going to see them in your final exam. And our final exam would be cumulative, meaning that we have like accumulative. I was like too drowned in the like different types of bonds, cumulative, conjugated, isolated, right? It would be accumulative, but it's the same root, you know, linguistically. Anyway, so now, so we denote arrangement of electrons with chemical bonds. So these bonds are actually electrons, right? So going back to benzene, we said that benzene has like this structure, right? And we also studied Kekule's structure for benzene, that we said not only we have this, we also have this structure, that double bonds alternate between, you know, here. So you see the difference of two structures. In one of them we have like the double bonds here, the other one here, right? So both of them exist at the same time. And both structures, Kekule argued that we have like this and this, you know, kind of in equilibrium. And we cannot say that benzene is purely this or this, is both of them. And these types of structures, as we mentioned, we call them resonance. So they are exactly the same, just the arrangement of electrons. You see that these electrons here, or like, let me have like blue. They can be whether here or here. So that's why we say the arrangement of electrons are different. But if we have like this description, this is good and nearly correct, but not entirely. Because if we have like, I tell you, I have this structure and this structure, you may think that we have at some point this structure, at some point we have this structure. But benzene actually have only one structure, and you know, imagine if these two structures were to exist at the same time, okay? So you don't have double bond, you don't have single bond, you have something intermediate, and then have one type of bond. Does that make sense? So that's why we say Kekule's model for the structure of benzene is nearly, but not entirely correct. And the part that doesn't make it entirely correct is the thing that I just mentioned, that these bonds, you know, it's not like that you have two structures and then they alternate. You have like one type of bond, okay? It's not single bond, it's not double bond. It's something intermediate. And I also wrote what I just said in the next slides, which is basically, as I said, from your book. Anything that I'm writing here is from your book, okay? And if we consider Kekule's structures, you see that they just differ by the arrangement of the electrons. And, you know, all the atoms, they have like the same positions, but, you know, different arrangement of electrons. And that's what we called resonance structures, or molecules that have resonance. Any questions? Okay. So now, so this is basically what I just said before. So we call these structures resonance. We say that benzene has a resonance hybrid structure. And we call it hybrid because we have like two structures and then it's kind of like something in between, kind of like hybrid, right? And instead of, so previously we wrote a equilibrium symbol between these two molecules, and we learned in chapter 1 that if we write like double-headed arrow, it shows resonance structures. So that's why now we write this type of arrow. And here, these kind of like curved arrows, it shows that this double bond, these electrons can also be here, right? Or these electrons can also be here, and the other one the same thing. And also for here, these electrons can be here, here, here. So basically we're emphasizing the resonance structure. Any question? And again, you know, as I said, when you want to make a presentation for like a job opportunity or like for grad school or any conference, you just should have like the picture and then explain so the audience listen to you, not reading the slides. But since I want to ask you in the homework and I want you guys to have more resources, I also write the text. So you have it as well. Okay, so this is basically, again, what I just said, that we have like the two structures, you know, at the same time. In other words, you know, all benzene molecules are identical. And as I said, the bond is hybrid between, like, it's not single, it's not double, it's something in between. And that's why benzene is more stable than either of the contributing calculase structures, okay? Because of what I just said, that the bonds are really stable because they kind of like, you know, because of the arrangement of electrons. And here, you know, I give these in your exam quiz, homeworks, true or false, so you should read these slides really well. Because if I say, calculate the structure for benzene is entirely correct, true or false? False, right? Because it's nearly, not entirely. Or if I say benzene has 3 single bonds and 3 double bonds, true or false? False. There are no single or double bonds in benzene. Only one type of carbon-carbon bond, which is some intermediate type. Okay. So, by the same rationale, if I give you this structure, and then I ask you name this compound, and I think I gave that in your homework problems too. So, so the answer is benzene, right? I hope we learned that this structure, you know, it represents benzene. But if I tell you the name of this compound is like 1, 3, 5, let me write 1, 3, 5, try, or like 1, 3, 5, and then I have like 6 video. Okay, it's going again. 1, 3, 5, hexa, try in. Okay, and remember, when we have like E and E, we mean that we have an alkene, we have double bond, in other word. And then tri means 3, like, and then remember, if you have 3 double bonds, you write 3 or tri here, okay? Now remember naming compounds. And then here you have 6 carbon, and then this is 1, 3, 5, okay? So this is a hypothetical structure. We don't have this structure in nature, okay? We call this a benzene ring, but when I write this, we know this is benzene. We know that we don't have 1, 3, 5 hexatriene. So hypothetically, we have this name associated with this structure based on what we learned, naming compounds. But we know as a fact, based on chapter 4 that we are studying, that this is a benzene ring. Okay, so that's why when we name this compound, it would be benzene, not 1, 3, 5 hexatriene. So theoretically, hypothetically, that is the name of that. But we know that benzene doesn't have double or single bond. That's why we don't name it like this. Does that make sense what I'm saying? Good? Okay. So now we're going to talk about resonance energy of benzene. And your book has a nice way of demonstrating resonance energy, and it's like a story, and I'm going to follow that because I thought it's really nice. So remember, again, these texts, that I wrote here, it can be true or false in your homework exam. A resonance hybrid is always more stable than any of its contributing structures. And remember, calculase structure for benzene, we had 2 structures that they were at equilibrium, they would exist based on what calculase said at the same time. So we had 2 structures, right? But resonance hybrid, which is the actual structure of benzene, is more stable than either of those. Okay? And now we want to basically prove this. And if we have an exam that it wasn't multiple choice question, I would tell you prove that resonance hybrid of benzene is more stable than its contributing calculated structure. But since I cannot ask that, I mean, I may give you like explanation, but I just should write like half a page to explain what I'm saying, A, B, C, D. But you should know this description and then this proof that I'm giving right now. And as I just wrote in the previous slide, if we consider one of the hypothetical structures of calculated structures, we have like 135 cyclohexatriene. Can everyone write this name here? Good. So this is basically the concept of chapter 3, naming compounds. So if you have any question how to write this, I'm going to go over it in tutoring sessions, and you're always welcome to just email me, stop by my office, or anything. So make sure to know how to name this compound. So now, before I prove it to you based on what your book said, I'm going to give you some necessary information. One thing is that, you should remember that hydrogenation of a carbon-carbon double bond is an exothermic reaction. This is another thing that I'm going to ask you in the exam. And anything that I teach in the class, obviously, I'm going to ask in the exam. Unless I tell you, you don't have to remember this number or this. So remember that when we want, to hydrogenate the carbon-carbon double bond, and hydrogenation, like halogenation, like chlorination, it means that our compound reacts with hydrogen, right? Hydrogen molecule. So that is hydrogenation. And that is an exothermic reaction, meaning that energy or heat is being released. Okay? And the number, this heat or amount of energy that is released is about 26 to 30 kilocalorie per mole. Okay? So I don't ask you the number, but if I give you this number, I'm going to ask you the rest of the things that I'm going to teach. If I give you like one basic number, you should be able to do the calculations based on that. And when I just teach, go through the next slides, it becomes more clear what I'm saying. But as of right now, I tell you this number is roughly 26 to 30 kilocalorie per mole, the amount of energy that is released when we hydrogenate, basically, this double bond. Okay? And the exact value, so I gave you a range, but the exact value depends on what structure I have specifically. So if I have methyl here, or bromine molecule, like bromo, right? Or depending on what substituents I have attached to these carbons, right? The amount of energy would be different, okay? And this is another thing. As I said, anything that I write here, you can think of it, and this is one way of studying for the test. Because sometimes you read through the slides, you think that you know everything. Each sentence that you read, you can ask yourself, what question I'm going to ask, right? So here, I tell you, the exact value depends on the substituents attached to the double bond. Okay, so I say, is the following statement true or false? The amount of energy released in halogenation of a carbon-carbon double bond is always 28 kilocalorie per mole. False, right? Exactly, because it's not an exact number. Depending on what substituent we have, this amount of energy can vary. Before I go to the next slide, any question here? Or I tell you how hydrogenation of a carbon-carbon double bond is an endothermic reaction. It's an exothermic. Energy is being released. Now, the other thing that you should know is that if we have two double bonds in a molecule, and two double bonds, if they are being hydrogenated, twice as much heat is being released or evolved. okay? So if you have like, again, if you have a compound that it has 2 double bonds for each of these, and this is where I can ask you questions. So if I tell you here, this amount is like 28 kilocalorie per mole, and I give you this structure, I say, what is the amount of heat roughly required to break the two carbon-carbon double bonds, considering for one is 28. Exactly, you just multiply this number by 2, right? And then kilocalorie per mole. So this is what I mean. So if I give you a compound that has 4 carbon-carbon double bonds, I give you the amount for 1 and I ask you for 4. So you should know that you should basically multiply this number for 1 carbon-carbon double bond, multiply that by how many carbon-carbon double bonds we have. Good? Any questions? Now I kind of told you, or like gave you like the required information that I'm going to ask here. So now what we're trying to do is to prove that benzene has a hybrid resonance structure, or like we have like, benzene has like 2 structures that they are hybrid resonance of one another. In other words, we want to prove that benzene doesn't have any single or double bond. Okay? So if we just consider, so you know that benzene in general, when we write one of the calculated structures, it has 3 carbon-carbon double bonds, right? And if you consider just the ring by 1 double bond, right? And we call that cyclohexene, right? Can anyone tell me why I didn't write 1 cyclohexene?
So it doesn't matter where it is and it starts.
Exactly, it doesn't matter, even if I put like this double bond, I'm going to write this here and then erase it. Even if I put the double bond here, if you just rotate the structure if you just rotate your notebook, or if I just like rotate my iPad, I have exactly the same structure. And then there is only one possibility, we don't write the numbers. We always love brevity, and we want to be concise because we're really busy to write 1. So we call this structure cyclohexene. Again, we have like double bond, right? E. We have 6 carbons, so it's like hex, right? And then we have a ring, is cyclo. Anyway, so if you want to hydrogenate this molecule, so I have it plus H2. And you should remember that hydrogenation is plus H2 because hydrogen is a diatomic molecule. Even if I don't say hydrogen molecule in exam, if I say hydrogenation, you should know that it's H2, okay? And I tell you that this amount of energy is being released, minus 28.6 kilocalorie per mole. And here is my energy scale, right? And now I tell you, if I have another, double bond here, so I call this structure now 1 and 3 cyclohexene. And we start here 1, 2, 3, right? And then I say 1 and 3 cyclohexene. And here I made a typo. So here plus 2 H2. Okay. So now if I tell you that I want to hydrogenate this structure, now we have 2 double bonds. Do you remember what would be the number, or what do you expect that number to be? Double of this number, right? This is what we just talked about. If you have like 2 double bonds, this amount would be double. So we expect 2 multiplied by 28.6 and would be, minus, if I consider this number being negative, would be minus 57.2 kilocalorie per mole. And scientists, chemists did this experiment and then find out this number exactly. And these numbers are fairly similar, right? Experiments with theory. So now if I tell you if I add another, double bond, how do you think the number would change theoretically based on what we talked about? Triple, right? Based on what we talked about, if you have now 3 hydrogen, so this was 2 hydrogen, here is 3 H2. We expect theoretically, based on the rule that I just told you, that we have this number multiplied by 3, because now we have 3 double bonds. But so we expect this number to be between minus 84 to minus 86 kilocalorie per mole. But when scientists, chemists did this experiment, they realized this number is almost minus 50 kilocalorie per mole. So it's much lower. Can anyone tell me why that is?
They're not double bonds.
Exactly, these are not double bonds. This proves that benzene doesn't have a double bond. Are you following me? Does that make sense? So if benzene had double bond, this amount of energy should have been minus 86 almost, 3 times that of amount of this energy for one carbon-carbon double bond. But benzene is much more stable, and you see, usually, all the times, when energy is lower, we have more stable structure. So if you look at it, here in the energy axis, you see that this structure right here has lower energy than this. So it's more stable. That's why benzene, the resonance hybrid structures of benzene is more stable than any of the hypothetical calculated structure, or even 1 and 3 cyclohexene. Does that make sense? Any questions? Okay. So this was this, and I'm going to find a way to ask you this in the exam. So as long as you know what we talked about, you can answer the question. Okay. If we deduct 86 from, this is roughly 50. And this is basically the summary of what we just talked about. Real benzene molecules are more stable than the contributing resonance structures. And as we said, the hypothetical 1,3,5 cyclohexatriene. And remember that this molecule is hypothetical. Doesn't exist. It's kind of just for us to know one of the calculated structure and name if the ring had 3 double bonds. And here, right, so here is the actual energy being released in hydrogenation, right? And then here is the hypothetical amount of energy being released. Okay, and this number would be 36 kilocalorie per mole. Okay, so if I give you the actual amount of energy that is being released and the amount of energy being released for one carbon-carbon double bond, you should be able to calculate this number. Does that make sense? Okay. And now this is what we call stabilization energy or resonance energy, which is the difference between actual energy of the real molecule, basically the resonance hybrid, and the calculated energy of the most stable contributing structure. Again, remember, we had 2 contributing structures, calculated structures, and then we have the actual molecule. The difference between these 2 energies would be resonance energy or stabilization energy. Good? Any questions? Okay, if no question, I'm going to go to the next slide. As I said, now we're going to talk about different types of reactions or like some types of reactions that we have in benzenes. I'm using your book and the slides, but it's nicer to just write it myself, I guess, maybe for myself. Anyway, so we have like this benzene ring, and we want to have like chlorination, right? So we want to react it with chlorine molecule, and we should have a catalyst. And I don't ask you for each reaction what catalyst we have. As long as you know that we have a catalyst, you're good. So if you write, and this is always what I do for myself, I write the expanded structural formula, so I know exactly what atoms I have and how hydrogens are attached to my hydrocarbon, right? So you see that I have like hydrogens attached to these carbons here, okay? And now I told you that we have substitution reactions, right? So what we do, we kind of like switch this hydrogen and this chlorine. I'm just like pressing on the thing that I wrote last night, hoping that palette changes. Anyway, so now this Cl comes here, and then this H goes here. Does that make sense? So it's fairly straightforward, right? So this is chlorination. So if I tell you in exam, write the chlorination for benzene, and I give you like 4 different options, you should like choose this one, okay? So in one of them, I just give you 1 chlorine atom, or like in one of them, I write benzene structure that has like 1 less double bond, so it's not benzene. Or like you saw the exams, right? I have like ways to make the options wrong. Or don't write HCl here, write like H radical or like Cl2.
Do we have to know what kind? We don't have to know what kind of catalyst, right? We
No.
just have to know that there is a catalyst.
Yes, exactly.
Okay. So we won't have to like pick between catalysts. Which
No.
one we should? Okay.
No, that is not the focus of our course. So as long as you know what is catalyst, that it increases the reaction rate and it's not being consumed in the reaction, as long as you know that, the rest of it, as long as you know there is a catalyst here.
Perfect.
Okay. Great question. Any other questions? Okay. So the next reaction, yes. Okay. Now the next reaction is nitration. And that is the one that can get tricky, because you may think that, nitration is the addition, basically, I don't use the word addition, so don't confuse you. You may think that one of our reactants here would be nitrogen or whatever else, So the reactant is like HNO3, okay? And I don't talk about like, I talked about naming acids and like, ionic compounds, molecular compounds in my 101 class, but in this class, I'm not going to ask you those, so you don't have to worry about it. I'm just going to give you the structure. For HNO3, as I just wrote earlier here, you can have like 1 NO2. Remember that we had like, nitrobenzene, we had like NO2 attached to our benzene ring, right? So now I write it somehow that I can attach NO2 to my benzene ring. So we have like, if I extract 1 NO2 from here, the remaining would be HO. Can everyone see that? So here, if you count the number of atoms, it would be HNO3, exactly what we have here, okay? And again, we have like catalyst, but different type of catalyst. And here, we substitute this hydrogen and this NO2. So we have the NO2 here, and then this hydrogen here. So let me write it here. So here, your, HONO2, if we, switch this hydrogen and this NO2, here you have like hydrogen. So what is HOH? Water, right? Is H2O. So you should just like memorize this reaction, which is nitration. But again, if you don't study, I give you things in the exam that they may make sense. So I have here plus N2, for instance. And then here I have N plus, I don't know, NOH or something else that would be wrong. So you should remember nitration is this reaction. Any question? Okay, let me now try to finish what I have here. The other type of reaction is sulfonation. Okay? And here your catalyst is SO3 and your other reactant is H2SO4. Okay? And again, here, this is kind of like just like memorization. I don't have a good way for you guys to remember this. I guess if you remember that the product would be water, and then you know that you have one hydrogen here, you extract one OH here, so you have water here, and the rest of the molecule would substitute this hydrogen. I think this is the best way to memorize this. If you remember that the product is water, right, and then you need an OH here to substitute with this hydrogen here. So this would be sulfonation reaction. Okay? Does that make sense? Question? Back to the end. Finally, or like second to last, is like alkylation reaction. And as we know, alkyl groups are like, CN, H2N, basically alkanes that they lost a hydrogen, so it's basically CnH2n plus 1. So if you have like C1, H2 plus 1, CH3, or like CH3, CH2, methyl, ethyl, right? Those good things. So now alkylation is when you have your benzene reacting with RCl. Okay, and this R, as we said, can be an alkyl. It can be methyl, it can be ethyl, depending on what we're dealing with. That's why we call it alkylation. We don't call it like methylation or like ethylation, because it depends on what ethyl group we have here. And then again, we have a catalyst, different type of catalyst, but we have a catalyst. And what you do is that you just, switch these two guys, right? So here you have R attached, your alkyl attached to this carbon here, and HCl. So this is one type of alkylation reactions. Good? Any question? So if you just remember that the reaction is substitution, and then you know what part of molecule you should substitute with this hydrogen, right? So you should remember that you substitute this alkyl with this hydrogen, not Cl. Okay, so your product would be HCl, not RCl. As long as you remember that, the rest would be the same for all steps, for each of these types of reactions. Just go. But we have another type of alkylation reactions too. And this is like more industrial, and I guess that can be tricky, because in this case, you have like your whole structure that you substitute this hydrogen with the whole structure. Okay? And the reason that you don't, I just write this here so I can erase it after I write, because it's not entirely correct. And the reason that previously we were like substituting part of our molecule with this hydrogen, right? And then add this hydrogen to the remaining of the molecule, So in this case, we don't do that because of the structure that I draw that I drew here. So if we have, so what do we call this molecule here that I wrote? So this is like C2H4. Ethene, right? So when we react this ethene molecule with this benzene here, what we do, again, we substitute, this hydrogen with, this structure, and, so here, till here, C2H4, right, is the molecule that we had, right? It's kind of, right? And energetically, it's not favorable to have like this hydrogen by itself, or like, we cannot have, if I don't have this part of the molecule, I cannot erase this because I wrote this last night. So, but if I don't have this part of the molecule, right, this structure doesn't make sense. It's not energetically favorable because I need to have one more hydrogen, okay? So, or like this structure also, this is not energetically favorable, okay? And then as you see, if I put like this double bond here and then this hydrogen, if I write it as such, like what we were doing before, 1, 2, 3, 4, 5. Now this has 5 bonds. So any other alternative is not favorable. That's why we just have like this hydrogen being attached here, and we have like this structure. Does that make sense? But this reaction still is a substitution reaction. This is important to know because we're dealing with benzenes. Benzenes don't go through addition reactions. This is also a substitution reaction, and specifically is alkylation reaction, okay? Any questions? And as you see, this part of the molecule, this is C2H5, and this is an alkyl, right? Good? Any questions? Okay. Now we talk about, and finally, we have like alkylation reactions. And then I'm going to talk about more. In the next chapters, I'm going to talk about carboxylic acids and all that. But as of right now, you just remember these types of reactions we call alkylation, that we have like RCO, this type of group that is attached to Cl. And then what you do, you switch these two. And then you have like RCO attached to your benzene, and your hydrogen here attached to Cl. So you have HCl plus the rest of the molecule. And then you have a catalyst too. But as I said, you don't have to remember the name of the catalyst. Any questions? Good? Yes.
So in most substitution reactions, there is 2 products.
Yes.
But for the alkylation that we just did, it's just 1.
Exactly.
Okay.
Yeah. Great point. Okay. This, I also included the part of the book that has these reactions, basically electrophilic aromatic substitution. And remember, in benzenes, we have, and in aromatic compounds in general, we have substitution. Remember, because we don't have double bonds, so for that matter, we don't have addition reactions. Do you remember? What was the difference? So how do we write, or how did we write addition reactions for alkenes? Can anyone explain it to me? So if I have an alkene, right, if I only have like, 1 double bond, right? And then, yes?
The addition would break the bond.
Exactly. So for addition, we would break the bond. So for instance, if this was plus HBr, we would break this bond, and then we attach hydrogen on one side and Br on the other side, right? Remember? And this was addition. And then how did we decide which part of, whether attach hydrogen here, Br here, or vice versa? How did we decide? What rule did we use? Markovnikov's rule. And can anyone tell me what was that rule?
You attach the most positive molecule of what you're adding to the carbon that has the most hydrogens.
Exactly. So you attach, basically, to paraphrase what your friend said, if you have HBr or like any molecule, right, that you're adding it to your alkene, one part of the molecule is more electropositive. And in most of the examples that we talked about in the class, it was all, it was hydrogen, because we had like HBr, HF, HCl. In all of those, hydrogen is more electropositive. Your halogen is more electronegative. And you would count the number of, so in your original molecule with double bond, you count the number of hydrogens that are attached to each carbon in the double bond, and whichever had more numbers of hydrogens attached to it, you would attach the most electropositive part of your molecule, which was mostly hydrogen, to that one, to that specific carbon. In this example, they are like the same, so it doesn't matter which one you attach, right? Because you have like one hydrogen here, one hydrogen here. But in some examples, they weren't the same. Are we good with this? Okay, so now if you accept from me, based on what your book said, that we have substitution reactions in aromatic compounds. And here again, I have everything that I just wrote in each slide individually here as well. So make sure to study them. And also here, I wanted to have like, again, extra credit activities, but since we don't have time, I just go through them in like, 1 minute. So if you want to write the structure of cyclobutylbenzene, again, remember that this was here was like cyclobutane, right? And then if you have like cyclobutylbenzene, you have like one benzene attached to one of these carbons, right? So this would be cyclobutylbenzene. And benzyl iodide, remember how to write. This was benzyl group, and you should know that for your exam, okay? And then benzyl iodide is basically this group attached to one I here. So when you attach it, this would be benzyl iodide. And then let me see and then here is just like explanation of what we talked